Okay, thank you very much for the introduction. Can you hear me well?
Yes.
Okay.
Yes.
Okay. So first, I thank the organizers to invite me to give a talk in this conference. So, uh, so I think the reason I was invited is that I joined the book project of him with Ahmed Abes, which was published in 2016, I think. And yeah, actually, that project was yeah planned by him and Ahmed Abes, and afterwards, they kindly invited me to join their products, join their plans, and so I'm very happy. Uh, Finally, yeah, I got happy with that. And in this occasion, I'd like to thank it again. And also, we have started some collaborations, and I hope that we will continue our collaborations also in the future. Okay, so now I think I will start my lectures. Okay, so today I think I will talk about something about the Nygaard filtration on the prismatic cohomology with coefficients in crystals. So prismatic cohomology is introduced by Barth and Schulze. Maybe the paper is put on archive maybe around 5 or 6 years ago, and now it's quite famous. And so the crystals and their cohomology on this prismatic theory can be described in terms of q-Higgs modules. Here, so q-Higgs modules means q deformation of a p connection. And in this talk, I will try to explain how this description gives some understanding or some computation of Rham specialization or Nygaard filtration of the prismatic cohomology with coefficients in crystals. And if the base of the prismatic cohomology is defined over q-crystalline prism, which means that parameter q is given on the base. So in that case, so some geometric q-Higgs modules appear, and it's relatively easy to compare it with some Rham specialization by taking some reduction modular analog of p, a q analog of p, and so on. But if the base field does not have a parameter q, in that case, by adding a parameter q to the base, then we can describe crystals by adjoining some q derivation with respect to q itself. And and in that case, so q-Higgs field is non-commutative in nature. So we have geometric q-Higgs field and arithmetic one, and they don't commute each other. So it's not obvious that Rham specialization can be described in terms of such non-commutative ones. So I will try to explain how, but the answer is it's possible, and I will try to explain it in this talk. Okay. So okay, so to begin with, I will first explain what is this q-Higgs modules or q-Higgs field. And I first start with some simple example of twisted derivations. So let R be a ring, and Q is an element of R, and I always denote by mu the Q minus 1. And so if you're given Q, so mu always means Q minus 1. And here I assume that R is mu torsion free. And consider the polynomial ring over R, and I denote it by A, and consider this endomorphism of A defined by T goes to the T times Pth power of Q. And then it is easy to see that the image of A under gamma minus 1 is contained in the ideal generated by mu. And since we assume that R is mu torsion free, where we can divide this gamma minus 1 by mu and obtains an endomorphism of A. Okay. And then just by definition, you can easily compute the image of nth power of t under this operator. And the image is like this. So the nth power of t times this q analog of Pn. And here q analog of Pn is just this quotient. So nth power of q minus 1 over q minus 1. And so this is easy to see this because if you apply gamma to here, so you get p nth power of q. And so if you take a difference and divide it by mu, so you get this one with m is equal to Pn. And this one is just a sum of 1 plus q plus dot dot dots plus q to the m minus 1. So if you take the reduction modulo mu, so the mu is q minus 1. So then, so this becomes just m. So if you take the reduction modulo mu of this operator, so you get, so this becomes just Pn. So this operator is equal congruent to the p times logarithmic derivation. So theta is a q deformation of this logarithmic derivation times p. Yes. And so this operator satisfies a relation coming from this relation. So gamma is an endomorphism. So we have this equality, and but gamma is 1 plus mu theta. So this and mu is torsion free. So this is equivalent to this equality. So it's easy to compute. So theta times AB, the image of AB under theta is equal to theta A times B plus A times theta B plus mu times theta A theta B. So if we don't have this is a usual derivation, but here we have mu. So that's why I call a twisted derivation. Yes. And also we can consider an analog of so we can consider twisted connection over this theta. So if you are given a mu torsion-free A module M, and if you have a gamma is this endomorphism. So if you have the gamma semilinear map such that the image of gamma m minus 1 is contained in mu m, so then using this mu torsion freeness, you can define the operator theta m in similarly as before. And then, so the semilinearity of this map implies some twisted Leibniz rule like this. So just by, again, putting a 1 plus mu theta m in here, so you get this equality. So the image of AX, A is an element of A and X is an element of module. So then the image of AX under theta M is A times theta MX plus theta AX plus mu times theta A theta X. Yes. And if we don't have this is a usual connection over this theta. And so this is twisted by mu. And based on this observation, I define a mu derivation over a ring as follows. So A is a ring, and Q is an element of A, and mu is as before Q minus 1. And so I just define a mu derivation on A is an additive map from A to A, satisfying the equality like this, the same equality of theta as above. So the image of AB is the same as, so this derivation of A times B plus A times derivation of B plus mu times both derivation. Yeah, so it's quite simple, but I use it. I use this derivation to describe crystals. Okay, and then so similarly, we can define some twisted connection over this mu derivation. So let M be an A module, and then connection on M with respect to this mu derivation, so partial, is an additive map, just additive map, satisfying the same equality as above. So the same equality. So if you apply this operator, so then you get A times the image of the under operator and so on. So the same one. And so here we don't assume that A, and we don't assume that A and A M are mutation free. So this can have mutation to define this. And if you define like this, so then if you define gamma and gamma M to be the identity map plus mu times this partial, and also so identity plus mu times partial M, then you get the ring endomorphism of A and gamma semilinear endomorphism of M. And if yes,
definition, is it does it follow? Is it assumed in addition that round day of one?
Yes, I'm sorry. So yes, you're right. I think I should add a condition on the image of one. Yes, yes, I think I forgot. Yes, you're right. I don't remember so well, but yes, yes, at least this is necessary, and maybe so zero is so this is additive map. So I think this is necessary. Is this your question or it's okay?
Yes.
Thank you. Okay, so then we also need some compatibility of this mu derivation with a delta structure, because so this is necessary to extend mu derivation to certain prismatic envelope. So the compatibility helps to extend the mu derivation. So I introduce the compatibility with delta structure. And okay, so then the delta, I will recall this delta structure quite briefly. So this is a map from A to A for a ring A, such that the map from A to the P typical bit ring of length 2, defined by X to defined by sending X to the pair of X and delta X, is a ring homomorphism. And if this is a ring homomorphism, you can easily see that the map defined by sending X to the Pth power of P plus P times delta X is a lifting of Frobenius. And if P is, if A is P torsion free, so actually the lifting of Frobenius and delta structure has there's a one-to-one correspondence. You can recover a delta from phi just by taking a difference between phi x and Pth power of x and divided by P. So, but in general, of course, we cannot recover delta from phi. Okay. And if and for the compatibility, so if delta Q is 0, usually if we consider the Q deformation of connection, we usually assume that delta structure satisfies this. And then we can define a certain compatibility of this mu derivation with the delta structure satisfying this, and such that it's the compatibility implies that the endomorphism gamma of A is a delta homomorphism. And actually, so this compatibility is equivalent to that gamma is a delta homomorphism if A is mu torsion free. So this is so compatibility. And I think if I have time, I think I can explain how this is defined. And yeah, okay. So I consider a finite ring over A denoted by E mu A, which is just simply the quotient of the polynomial ring in one variable by this polynomial t squared minus mu t. So, and then by sending x to x plus partial x of t, you obtain a ring homomorphism. So you can check easily that this condition is equivalent to say that this map is a ring homomorphism. And we can define the compatibility with delta structure by introducing a certain delta structure on this ring. And so the delta, we can define a delta A algebra structure, which means that this is a delta ring and the delta structure is compatible with that of A. And such that the image of delta T is some element eta times T. And eta is this quotient, delta mu over mu inverse, and this is actually an element in this polynomial ring defined by this formula. Yeah, you can easily show that delta mu can be divided by mu inverse if delta Q is equal to 0, and you can define an element in here. You can write down the explicit formula also. And then, so just this compatibility is defined as requiring that S is a delta homomorphism. Okay. And I use this description also to study the extension of mu derivation to some étale algebra or some prismatic envelope. Okay, so now I will go to prismatic crystals and q-Higgs modules. So if any questions, is it okay?
Yeah. Yeah.
Okay, so then I think I will try to explain how the prismatic crystals can be described in terms of q-Higgs modules. And okay, so we consider a bounded prism. So this is I just give a definition. So bounded prism is a delta ring endowed with an invertible ideal, satisfying these three properties. First property is just that R is I-periodically complete, classically complete. And P is contained in the ideal generated by I and phi I. And actually, under this completeness assumption, if R is if R is principal, so invertible, so it is locally principal. But if this is globally principal, so this is equivalent to so if I is generated by one element, so then principal, so then this condition is equivalent to the delta of D is unit. And the last condition is the p power torsion of R mod I is the exponent is bounded, which means that this is equal to p to the n torsion point for n sufficiently large. And this implies that R mod I is periodically complete, classically. And we need this property to define a prismatic site and prismatic cohomology and so on. Okay, so the most important example in this talk is this q-crystalline prism. And so this is a formal power series ring in variable q minus 1 with coefficient in ZP. And the ideal I is generated by q analog of P. And the data structure is defined by, in this case, this is P torsion free. So to give a data structure is equivalent to giving a lifting of Frobenius. And we consider a lifting of Frobenius defined by phi q equals to pth power of q. And then delta q becomes 0, as I mentioned before. And so PQ, so this PQ, the Q analog of P is actually the cyclotomic polynomial for Pth roots of unity. So if you take the quotient, you get the ring over the P obtained by adjoining absolute primitive Pth root of unity. And so this is P torsion free, so this satisfies this condition. Okay, and you can also check this for this PQ, P sub Q. Okay, so then so as a base of a prismatic site, we take a bounded prism, and I also use this notation I tilde, which is the ideal generated by I and PR, which this appears in here. And I assume that I is principal as before. And I assume that also, yes, we have a map from this ring, this quotient, to this R bar. R bar is defined by R mod I here. And throughout this talk, in the rest of this talk, I always assume these two conditions. Of course, if R is defined over this ring, of course, if you have a map from this to R, so by taking the quotient by this, you get this map. So, yeah. So, okay. But here I don't assume that there is a map from map of delta ring between this no map of prism from here to here. I don't assume this in my talk. Okay, so then so I only give a local description, so I consider a fine periodic formal scheme over formal scheme of R bar with periodic topology. So this is periodically complete, so you can consider formal scheme and consider periodic formal scheme. And to describe crystals, I take this diagram, commutative diagram. So since R doesn't have an parameter Q, so I add a parameter Q by tensoring this ring, this prism. So this is Q minus 1, so I just add parameter Q. And then we have a map from tensor product to R bar by sending one tensor Q to zeta P, because because we assume that by using, so I choose one homomorphism from here to here. And using that, we can define a surjection here. And then I take, as in the crystalline cohomology theory, I take some ring B over this tensor product, and assume that we are given some units in B such that G modulo the tilde lives in here and mu lives in here. So modulo this one, this becomes smooth, and so these units give coordinates modulo this ideal. And I also assume that B is given delta structure such that delta Ti is 0. So Frobenius sends Ti to P's power of T. And okay, so and then I assume that there exists similarly to PD envelope. I assume that bounded prismatic envelope. I consider envelope by taking kernel of this map and then take envelope. But I don't know, maybe it's not true that there always exists a bounded prismatic envelope. So I assume this. But for example, if this is a lifting, so A is smooth over R bar, and this then in that case, envelope always exists. Yeah. So later, I will only consider the smooth case. So and I compute the Rham specialization using lifting. So then this assumption will be satisfied. Okay. Okay. So then under this situation, we can define mu derivation of this envelope as follows. So this is simple. So and the same shape as so I consider derivation with respect to the parameter q. So I put T0 is equal to q to define the operator simultaneously. Okay, so the first claim is that there is a R linear mu derivation on B for I is the lies between 0 to D and compatible with data structure such that the image of Tj is Ti times Q analog of P if J is equal to I and Tj if J is not equal to I. So this is the same formula as I give before, as an example. And if you consider the associated endomorphism of algebra, so then R algebra, so then the formula becomes Tj goes to P's power of Ti times P's power of Q if J is equal to I, and so no action on Tj if J is not equal to I. So note that, yes.
Do you assume that B is complete for this addict topology you consider? So you said
yes,
but it should be
thank you. Yes, thank you. Yes, I forgot. Yes, thank you very much. So I have to assume this. Yes. Thank you very much. Yes. Okay, so otherwise we cannot extend, because the assumption is just so smoothness is assumed only after taking the reduction. So so to obtain a map on the whole P, so we need a completeness. Yes, and then this can be this mu derivation extends uniquely to a mu derivation on this envelope. And this is compatible with the delta structure as before. And to prove these two claims, actually, I use a description of mu derivation in terms of this delta ring homomorphism. And once we have this description, it is relatively easy to extend the mu derivation along a tile map or by using universality of prismatic envelope, you can extend mu derivation on B to delta using the delta structure on this E mu, in this case, E mu A, E mu B, and E mu D. Yes, it's simple. Okay, so then the most difficult, this is relatively easy, but the difficult part is the relations between them. And if theta I is theta pi or theta di, then if I and j is not equal to 0, so then this operator commutes. So this corresponds to the fact that gamma I, gamma j, so this gamma j, gamma I. Of course, if D is mutation free, this is equivalent. But for theta I, for positive I, and theta 0 has a non-commutative relation, and this is a bit complicated, like this. But of course, actually, corresponding relation for the endomorphism algebra is quite simple, like this. So yeah, so uh, is this correct? So I may have made mistake. Yeah, so I'm sorry. So this is wrong. Hmm. So I understand. Gamma 0, I, and 1 plus P. Yes. So if gamma 0 is an automorphism, this is this formula. And so this is quite simple, but if you take the associated mu derivation, so this is very complicated. And so then, so here I will try to explain of what's this and this. So di is defined by this complicated formula, but this is associated to theta I. Yes. And so, and then, so theta I tilde is defined by this formula, but this corresponds to the 1 plus pth power of gamma I appearing in here by this formula. So here, gamma 0 mu appears, so it's complicated. Yeah, because this non-commutative relation, it's not so easy to understand. And so 1 and 2 is easy to study, but for this one, so high power of theta I appears, so we need some work to check this relation. And I have one remark that this relation is complicated, but if you take the reduction modulo I and mu, so I is in the base, I is here and mu is here, and if you take the reduction modulo I and mu, then this strange operator disappears, and so theta I tilde becomes theta I, and so this becomes, so theta 0 and theta I becomes commutative. Yeah, and so we just have a commutative relation. It's become simpler, but if you lift to the whole, lift to the R tensor ZP mu, so we have this relation. Okay, so now as I'm almost ready. I'm ready to introduce q-Higgs modules on this prismatic envelope, and so by the definition is as follows. So D module is a little bit confusing, but not a D module, so the so-called D module, just a module over the ring D. And the q-Higgs field on M is just a family of theta di connection, which I defined at the beginning on M, satisfying the same relation as theta I. So we have two relations and the commutativity for positive I and j, and this relation for theta I and theta 0. Okay. And then I will also define associated complex. So I call it q-Higgs complex of this non-commutative q-Higgs field. And I define this as follows. So I define the theta under bar plus and theta tilde under bar plus as the operator consisting of positive I. And then these operators are commutative with each other, so you can just define a Kosovo complex using this operator. So this tilde is defined in the same way as this one. So we can consider this complex, and I denote it like this, looks like a Rham complex by defining omega formally as a direct sum of zeta omega I, and this is just a formal basis. And then we can define complex. And using this theta zero, we can define a map of complex like this. And the first one is the given theta m0, but by the non-commutativity, we have to twist the theta zero, and it's complicated, but I will try to give the explicit formula for this one, how this looks like in here. And then after defining this morphism complex, I defined this q-Higgs complex as a mapping fiber of this map, theta m0 dot. And okay, I will try to explain theta 0r for degree r. So I take the subset of this positive index consisting of R elements and define omega sub I to be the wedge product of omega I1 to omega IR. And I just define an image of x omega I under this map to be the theta 0 minus di of x times omega I. And d sub I is defined by this formula. This looks complicated, but actually this is, if you consider 1 plus mu di, so this is a product of 1 plus mu di for this chosen index. So in some sense, I take minus 1 and take 1 over mu, and then you get this. And then you can check easily that this gives a morphism complex. Okay, so now I can state the theorem describing crystals on the prismatic side of this x is a formal spectrum of A over R. So I recall that I tilde is I plus PR, and the first claims that crystals of O modulo I tilde nth power of I tilde modules on the prismatic site. I'm sorry, I don't recall prismatic site, but this is isomorphic. This category is equivalent to the category of the Q convergent q-Higgs d modules M satisfying this property, that is the underlying module is annihilated by the nth power of I tilde. Yeah. So this is the first claim. Yeah. So the second claim is that if you take suppose that we are given such crystal and consider the corresponding non-commutative q-Higgs field, then the derived projection of F to the risky side of X is just given by q-Higgs complex, sheafified version of q-Higgs complex of M theta M. So this is so since we work up modulo this ideal, so this is just topology is discrete. So this is a quasi-coherent module on this scheme with some the operator. Yes, the operator can extend to this sheaf easily. Can be extended easily. Yes. Okay, so this is a description, and I give some remarks on this one. The first, so we can also consider the absolute case. So there is an analog for absolute prismatic crystals when we have a map from this CP zeta P to this ring A. Yeah, by adding a parameter Q and so on. And actually the case A is equal to this ring, so was, or maybe more generally a bit ring of perfect, so I think it's better to keep perfect field of characteristic P. So then in this case, so this description was proven by Groll, Rushdum, and Kiros. And actually, recently I tried to remove this assumption. Yeah, so this I don't want to have this primitive p-stress of unity. Actually, we can also give some description by considering the action of p minus 1 roots of unity on here by sending q to the 8th power of q, and a is p minus 1 roots of unity inside here. Yeah, but I don't explain this here. Okay, so now I'm ready to explain how this non-commutative description gives description of Rham specialization of certain crystal on the prismatic side. So yeah, so maybe I will start another thing. So I think I will ask. So if you have any questions, I will answer. Any questions on here?
I think it's fine. Yeah.
Okay. Okay, so now I will try to explain explain Rham specialization. So I will try to explain first the precise setting we consider. So from now on, I assume that X is smooth or periodically smooth over this R over I. And I consider the module on this prismatic site satisfying these three properties. Yeah. And first, on each object on the prismatic site, the object looks like this. So we have a prism over this prism. And then taking the reduction modulo I, you have a closed formal subscheme, and we are given a map to X compatible with this one. So this is an object. And we give a flat topology on this site. And then I assume that, so before I assume that F is torsion free over killed by some power of I tilde, but here I assume that this is I just assume that this is complete with respect to this ideal. And assume that if you take the reduction, then this becomes a crystal. And I also assume that if the reduction modulo this object P is flat over the reduction of R by this power of I tilde for all n, then I assume that the same is true for the reduction modulo power of n, power of I tilde is flat over R modulo power of I tilde. Yeah, of course, if this is a projective, finite projective, this condition is automatically satisfied. And then I take the F phi, another O module, and which is just defined by, so this is P is the object, the prism defining this object has a has a delta structure, and so it has a Frobenius lifting, and take just a scalar extension, and then you get another module, and we define a drum specialization using this Frobenius phase change. So F phi bar is just a reduction modulo F phi by d F phi. So D is not a differential. D is a generator of the ideal of the base. So I follow the notation in the paper by Barton Schultz. And I just define the drum specialization is just a push forward or a drum specialization of F by push forward of F phi bar under the projection to Zariski site. And then so the first proposition is that if you define like this, so then the higher direct image of F underbar F bar phi is isomorphic to M drum tensor omega M of X over R. And then, of course, it is natural to construct a differential map or connection on here by using description. And so we consider this exact sequence. So this is D-torsion free by assumption on F. And so we have this exact sequence, and we take the boundary map. Then if you consider this boundary map for M is equal to 0, actually this becomes an integral connection. And so boundary map for M can be identified with this differential map induced by this integrable connection through the isomorphism. Yes. Okay. So then I think I will try to explain how one can show this by using q-Higgs module, non-commutative q-Higgs modules. So to do that, I consider the special B. So actually, I first take a smooth lifting of A over R like this. And suppose that the coordinates T1 to TD is given coming from here. And we consider the base change of this one to the base change. And we consider the I tilde mu completion of the C tensor ZP mu. So I add the parameter Q here. Yes? Okay.
Actually, I have a question.
Yeah.
Excuse me, does this connection satisfy Griffith's transversality with respect to some filtration inherited from the prism?
Let's say it again. So,
Does it satisfy Griffith's transversality with respect to some filtration?
yes. I will explain later. So this is the next topic. Yes. Thank you. Yeah. Okay, so I think I would try to okay, so to explain how one can show this. So first, starting from F by using theorem 3, the first claim of theorem 3, applying the theorem 3 to the reduction modulo, the reduction of F modulo power of I tilde, you get some module M on this formal scheme with the q-Higgs field. And actually, the underlying module is just the sheaf on this formal scheme. So this is an object on the prismatic side. So you can define the sheaf on here by using this sheaf on prismatic side. And this is actually equal. And then, so by theorem 3, the second claim of theorem 3, so the projection we want to understand is just given by the mth cohomology of the q-Higgs complex modulo D. So D is actually so an element in here. So so this non-commutative q-Higgs field is R linear. So so you can take just a quotient by this element D. And then since we take the Frobenius twist, and then we see that the q-Higgs field on M for positive I is congruent to 0 modulo D, actually. So it disappears. So it's easy to compute it becomes easy to compute this cohomology. But on the other hand, so for this arithmetic mu derivation, so if you take the reduction modulo D, so this becomes actually surjective. And using this, we get this simple description of this higher direct image of f bar phi. Yeah. So theta I for positive I disappears, and we have this short exact sequence. So this is m modulo D tensor omega r and m modulo T tensor omega r. And so this is a reduction modulo theta 0 r modulo T. Yeah. Okay. And then we want to compute this. But actually, if in the case r is equal to 0, so this becomes theta 0. And in this case, actually, so in this case, so since we construct this B from C, and using this construction, and actually theta 0 is C linear over here, and you can show that actually easily that the kernel of this map, in the case of R is equal, the kernel of this map is just the evaluation of this prismatic sheaf on this prism, on this object. So this, I'm sorry, so let me see. So where is yeah. So this is actually also an object of the prismatic size. So you can evaluate f phi bar on C, and actually it appears in it's quite natural to expect this. Okay, so where it is? Okay, so evaluation of this on C appears. Yeah, and C is a lifting of A, so it's quite natural. Yeah, yeah. And so, but for theta r, so if you take the reduction modulo D, actually this becomes like this: theta 0 times some element of ZP zeta P. And this does not depend on the index set I. And I use the fact that the theta I is trivial modulo D. And so in the definition of, I'm sorry, so I have to go back to the definition formula. So we have this complicated formula, but so if n is bigger than 2, theta I remains, and this becomes trivial modulo D, so this disappears. And if you take the reduction modulo D, so you can just simple computation, you get this formula. Yeah. So for general R, so I made a mistake here. So I'm sorry. So this is R. Then we have so we want to compute actually we want to compute the kernel, and actually also I want to also prove the surjectivity. And so then but this is complicated, but actually if you multiply D inverse Q analog of P, the Rth power, so this is a unit inside D. actually. And then, and also this is, we have to apply gamma 0, but similar unit. And then this just becomes, this becomes just theta 0. And so this multiplication, actually the kernel becomes m dram tensor omega r. So the original operator theta 0r is complicated, but if you take the reduction module d, and if you twist by this, then this becomes just this one. And I have to explain here, so why this is a unit. And actually, so d is a, okay, so prism over, of course, I, but also this is a prism over ZP mu. And by the rigidity of the prism, so actually, so d times capital D is equal to this P sub Q times D. So in some sense, I just replace D by PQ, and then this simply solves the problem. So it's a bit, actually, so the computation is a little bit complicated, but finally, this becomes simple. And then once we have this, the Bochstein map is easy to compute by just taking a lift into modulo square and taking boundary map, and then you can check the plane, on this. Yeah. Okay. Oh, okay. I only have 5 minutes. So, sorry. So, but maybe I think I can. How many? Okay. So 1 page plus something. Okay. I will try to explain quickly. Okay. So then, so I think I will try to explain Nygaard filtration. So so then I consider L eta D of this projection of F phi of RU star. And this is isomorphic to eta D of the q-Higgs complex by the second claim of theorem 3. So I just skip the definition. Yes. Okay, also eta D. And so it is not, actually, so it is naturally expected that the projection of the original F to the risky side is isomorphic to this complex after taking the Frobenius. So it is natural to expect this by some reason. And actually, I thought that I succeeded in prove it, but I found a mistake when I was preparing my talks. So this is just a plan now. So okay. So then so I want to define a hopefully I want to define Nygaard filtration here, but I just define a filtration here in my talk. And okay, so okay, so suppose that we are given a Frobenius isomorphism from F phi to F. So this is linearized, so this is all linear. And assume that this is an isogeny with respect to D. And then, as usual, we can define a Nygaard filtration of F phi as an intersection of F phi and R times phi inverse of F. We have two lattices. We have F and F phi, and we define filtration of F phi by using this another lattice. And I take the quotient, or maybe, so this is I take the image of this one in this quotient, and this can be also described in terms of this, like this. And we can define a filtration of Rham specialization by taking push forward of this one. And then, so so I have here's an answer to the question of if this transversality, you can prove that this satisfies this property. And furthermore, so you can define a Nygaard filtration on this one, on this q-Higgs complex, which is isomorphic to this one, and I expect this is isomorphic to this one, and by using this Nygaard filtration on M. So M is actually defined as a sheaf on D associated to this Sheafson prismatic crystal. So this has a Nygaard filtration. So I just define Nygaard filtration on this, but like this. So so element of nth power of d times r minus nth filtration, and takes the element here, and the image under the differential map lies in the n plus 1th power of d, and here's r minus n minus 1. So I don't explain why I consider this, but the important point that if you define like this, and then taking the quotient of nr by d times nr minus 1, then you can compute the this cohomology using this a kind of filtered Bochstein complex, and so I don't have time to explain, but and I also don't prepare it, but anyway, so you get an isomorphism to this filtered Rham complex. Yeah, but basically what we did the similar argument for this one with the Nygaard filtration. Yeah, so we have this exact sequence with some filtration on here and here and so on. So you can then show that this also satisfies this property. And so thus we even starting from non-commutative one, but easily, relatively easily, you can deduce this commutative result. Okay, so that's all. Thank you very much.
Yes, well, thank you very much. Are there any questions or comments, remarks of kind?
Yes.
Yes.
Can you say a few words about the new p-1 action that you mentioned in remark 3 after theorem 3?
Yes, yeah, it's where it is. I think I will. Yeah, here. Yes, yes. Actually, yeah. So so a few words. Yes. So so basically I do the same. So if you're given a bar and A, and similarly okay, so I have to start from like this, yeah, in this case. And then I take just the tensor product, maybe some completion, yeah. And then, but in this case, we have to add theta p to this one by tensoring the p theta p, yes. And then take the envelope. And then, okay, so then I consider, so of course we have gamma I for positive I. So this is the same. And actually I consider gamma 0, which goes to q times, okay, some power of u. And u is in some sense generator, topological generator. And also I wrote also considers the action of mu minus 1 and some relation. And then you can describe so it's so, and using this of course for this one, okay, so for this one I just consider the action, but for this one I consider some mu derivation corresponding to this one. And then you can describe crystals, and actually, so if I am correct. So, so we have, let me see. So, yes. Yeah. So then using this, we can also define this kind of complex. But the problem is that if you, so in this talks, I just consider the U is equal to 1 plus P, but in this new case, U is not an integer, so we have to consider the infinite sum. But besides that, everything is the same, and then you obtain a description. But for the description of cohomology, actually action of mu to the p minus 1 does not appear. So actually, so this derivation is enough to show this formula. So I don't understand the reason, but I just do the computation and then and show proving certain Poincare lemma, and then and finally, so this does not appear. So for this part.
Thank
Yes,
you.
yeah, it's something like this.
Thank you. Any more questions? No?
Did you want to ask?
Yes, yes.
Are there certain settings where your Nygaard filtration splits and therefore you get differential operators from this Fox zero connection on MDR?
Sorry,
Are there situations where your Nygaard filtration?
Nygaard filtration here, yes. And what's the question?
Yeah, your Nygaard filtration on MDR, are there situations where it splits and then you get some differential operator?
Well, what do you mean by split? I don't understand this.
You have a map from M Duram to Bill 1 M Duram.
In drum?
Yes, you have a filtration on M Duram.
Yeah, filtration field and drum, and
sometimes you have a map from M Duram to some fill R M Duram. Bill 1 in general. I'm asking if there are situations.
I'm sorry, I don't understand the question well. So splitting, so in which situation we have?
Is this a subspace of M Duram? Okay, maybe.
Subspace of M drum
And do you have sometimes a map from M Duram to that subspace in certain situations?
Sorry, I don't I don't know. So sorry, so I haven't answered. So
if no more questions, then thank you very much. We thank the speaker again. 11:45.
I will let you see.
okay.
Okay, so thanks a lot. So we say goodbye.
Goodbye.